Hello, this is topic 4 on viscoelastic behavior of polymers. In this lecture we're going to talk about the viscous behavior of polymer melts. So before we get into polymers specifically, let's talk a little bit about fluid dynamics. If we imagine we have a stationary plate separated from a movable plate by a layer of fluid, and we move the plate on top by a certain velocity, there will be a velocity gradient from the velocity of the plate on top to the stationary plate on the bottom. That velocity gradient is given as the change in velocity divided by the distance or thickness of the film, also known as dV dx. The velocity gradient can be thought of as a shear strain rate, d gamma dt. Since the force produces a shear stress, we can give the following equation. The shear stress acting on the fluid is equal to the force over the area, which is equal to the viscosity eta times dV dx, which is also equal to eta times d gamma dt, or the shear strain rate. Many fluids are what we call Newtonian fluids, water being a classic example. Newtonian fluids are a simple case of the viscosity equation because eta is constant in this case. No matter how fast you shear a Newtonian fluid, its viscosity always stays the same, as shown here in this diagram. As the shear rate increases, the shear stress increases linearly, which implies that the viscosity must be constant over that range of shear rate. But many materials are non-Newtonian, especially polymers. In this case, if I plot the shear rate versus the shear stress, I get a nonlinear response. Some polymers and substances are dilatant, which means that they shear thicken. As the shear rate goes up, the viscosity increases dramatically, leading to higher shear stresses. Other substances like paper pulp, grease, soap, and paint are shear thinning, so that as the shear rate increases, the viscosity drops and there's less shear stress. And yet others start out with high shear stresses and high viscosity, such as thermoplastic polymers in the melt state, and express a shear thinning response upon the application of a shear rate. So as was said, shear thinning is when as the shear rate increases, the viscosity decreases, and shear thinning is when, as the shear rate increases, the viscosity increases. A good example is starch and water. If you mix the right amount of cornstarch with water, you can make a polymer solution that you can actually walk across without sinking in, because it's gotten thicker or higher viscosity with the higher shear rate of your steps. Polymer melts often exhibit shear thinning, but typically do this in the melt state above the melting point, and exhibit a form of shear thickening in the solid state between the melting point and the glass transition state. So why do polymers melt shear thin? Well, we don't really know, but the idea is that it's a lot like octopus arms. Imagine if we had a long chain and we grab one chain in the middle and drag it, we'd be dragging the arms behind it. As it moves, it has less contact with other chains because the chains are being dragged behind the head of the molecule. With less contact, there are fewer entanglements, and the polymer chains then move more easily. This turns out to be very important in most polymer processing techniques, specifically injection molding and extrusion, because of the very high shear rates at the nozzles and along the screw. So how do we measure viscosity in polymers? Well, first of all, we typically do this by immersing the polymer into a solvent in order to dilute it, and then extrapolate from the diluted polymer to what the polymer melt would be. There's two ways of doing this. The first is capillary viscometry, in which we measure the movement of the polymer up a capillary tube so that the intrinsic viscosity eta of the polymer can be determined from extrapolating the solvent concentration to zero. The intrinsic viscosity is given by the equation of K m bar A, where m bar is the average molecular weight of the polymer and K and A are material constants. More modern technology involves the rotational viscometer. In this case, a polymer melt is stirred within a container at a fixed shear rate, and we measure the corresponding shear stress, and from that are able to calculate the viscosity.